Let's look at how to solve PDEs, a very brief overview. So in particular, PDEs that we have looked at and methods that we have seen in this course. So, first of all, we have stuck with only homogeneous PDEs, and we have tried to do things in very simple cases, so in which this algorithm works. Step 1 is separation of variables. You count the number of variables that there are and you separate in equally many problems. Then you find one direction, one set of variables that structures the Sturm-Liouville problem. If this fails, then you go back to step 0. You split into sub-problems and you do the same. These sub-problems take care of the boundaries of your problem, and you want to set them in such a way that at least one direction has a Sturm-Liouville problem associated to it. Once you have succeeded in writing the Sturm-Liouville problem, then you solve it, and you use the solutions from the Sturm-Liouville problem to fix the constant that you retrieved from the separation of variables and solve for the other variable. Now that we have a countable set of eigenpairs from the Sturm-Liouville problem, and you have used the eigenvalues from the Sturm-Liouville problem to solve for the other variable, then you can combine these two information with the use of Sturm-Liouville theory. Special for the heat equation, the solution can be written as a sum of something that does not depend on t and something that depends on t. So the part that is time independent is the solution of the Laplace equation with boundary conditions. While the part that depends on time is something that tends to 0 over time and is called a transient solution. Why can you do this? Well, intuition about this, how this works, is that the heat equation is not conserving energy. So either you're gaining energy through the boundary condition or you're losing energy through the boundary conditions. Either ways, energy is not constant. So the part indicated by the transient solution is the part through which energy is dispersed or gained. This is not true for the wave equation. The wave equation maintains energy, so if there is an oscillation at some point, there's going to be oscillations all the time. You don't have a transient part to the solution. You don't have a part depending on time that tends to 0.